In this video, we'll be discussing some of the theory involved with calculating an ANOVA analysis. So we're going to begin by discussing some notation. We're going to let I represent the group number. So think I equals 1 means that the individual is going to be in the first group, and so on. I equals 2, I equals 3, I equals 3 would represent being in the third group. And this is going to be for I, total groups, capital I. J is going to represent which person within that group the individual is. So here, J equals 1 would represent the first person in the group. J equals 10 would represent the 10th person in the group. It's important to note here that the person within the group, we can have multiple people of the same number. So group 1 is going to have a first person in group 1. We're going to have a J equals 1 within group 1. But in group 2, we're also going to have a first person in group 2. So we're going to have a J equals 2 in group 2 as well. So we're going to need both I and a J to determine which person we're talking about, because we're going to have multiple first people. So the question then becomes, well, which group did you come from? So I'd be the first person from group 1 as opposed to just the first person. You'll note that because this is within each group, and this peaks out at capital J, sometimes this is called little n, but this peaks out at capital J, observations within each group. This assumes that each group has the same number of observations. Now, a lot of the things we'll be showing you within the theory section actually don't assume this, but for notational purposes, I'm going to keep this notation rather simple. If you wanted to expand the notation, you would use J, capital J sub I, to represent that each group I can have a different number of people in it. In this case, each group is going to have the same number of people, capital J. As I mentioned, we need both an I and a J to really distinguish which one we're talking about. Here, Y sub ij is going to represent the dependent variable observation for observation J in group I. So this could be the first person in group number 5, and this would be Y sub 5 comma 1 or 5, 1. This could be the 100th person in group 3, in which case this would be Y sub 3, 100. Now, I apologize. My little bar on the top doesn't display very well in text in PowerPoint here, but suffice it to say there's a little line on top of this Y. Here, maybe I can draw it with my pen a little bit better. There, that's a little bit better. There's a line going all the way top. This is Y I dot bar. Now, the dot means that instead of looking at any individual J, we're looking at all of the J's. Bar, if you recall, meant sample mean. So we're saying we're going to look for group I, and we'll replace this with a number when we actually get data. So for group 1, we're going to look at all the J's, and we're going to take the mean in group 1. Now, if you think about it like that, this becomes the average or the mean Y value, dependent variable, for group number I. And again, we replace this with a number when we get to actual implementation. So we'd have 3 groups, then we'd have 3 means, Y sub I dot bar or 1 dot bar for the mean of group 1, Y sub 2 dot bar for the mean of group 2, Y sub 3 dot bar for the mean of group 3. And again, we have a dot in place of J because we're not looking at any specific individual. We're taking the average over all individuals within that group. Similarly, we can have Y sub dot dot bar. And what this represents is if I don't just take the average over all individuals in a group, but I take the average over all individuals in all groups. So this is the average of every single darn data point you have. And we call this the grand mean. Again, this is the average dependent variable, that's Y, across all groups and all observations. Now, the total sample size here is capital I times capital J. That is the total number of people in each group times the total number of groups. Say I have 3 groups, each of which have 30 participants. I would be 3, capital I would be 3, capital J would be 30, representing the total numbers in each category. Multiplying them together, I would have 90 total participants. And that is sometimes denoted capital N. That's the total number of individuals within our sample in an ANOVA sample. Now, this is a bit deceiving because often capital N is used for the population size. But in ANOVA, capital N is sometimes used in place of capital J, or excuse me, lowercase n is sometimes used in place in capital J, which means that lowercase n no longer represents the total sample size. Instead, we use capital N. So just be aware of that notation in this context. Again, capital N is going to represent the size of the total sample. And if you ever see a lowercase n in the context of ANOVA, typically it's the sample size per group. All right, so we're going to jump into one more piece of theory, but actually first let's do a graphical view of our notation, and then we'll jump into this theory. So we're going to look at different components of a multi-group analysis graphically. Let's see here. All right, so we've got our three groups. This is the image that we saw in the last lecture video. We have the specific points. So this top point in general, we call Yij. In this particular case of the top point, it was the 9th observation. And it's not ranked by height. It's just how many people are in. I believe this has 10 dots within each group. I'm not going to count them, but that's just my memory. And this is group number 3. So how we would denote this is Y sub 3, 9, indicating group number 3 and person number 9 within the third group. And again, we've got 3 participant number 9s, 1 for group 1, 1 for group 2, 1 for group 3. So this is participant number 9 from the third group. All right, so those dotted lines, which represented the group means, now we have the notation for them. This is going to be, in general, yi dot bar, but in this specific case for the third group, y3 dot bar, representing the mean of the third group. We didn't have this earlier. I'll draw it in our kind of gold here. But in this case, this represents the grand mean, or the mean of all of the data points, and it is denoted y dot dot bar. All right, so let's jump into our last piece of theory that we need. So the process in ANOVA, recall, is to analyze variance. And the fundamental ANOVA identity helps us to break this variance down into the components that we eventually analyze. So let's see how this works. To start, I want you to consider the total point movement from the mean to the individual point. So this represents, at some level, a base measure of variability. Now, we can't use this because if we added all of these up, one of the properties of the mean is that they would all add up to 0. So if you recall in the variance equation, we squared this before adding. But here, this is saying how different is every point from the grand mean, y sub ij, every individual point, minus y sub dot dot bar. Again, I apologize, my bars aren't showing very well here. And is asking again, what's the movement from each point to the mean? All right, so we're going to play around with this equation just a little bit, play around with the total movement or variability. What we're going to do is we're going to add a special version of 0 in the middle relating to the group mean. So up top in that first equation, we have the point and we have the grand mean, but we don't have anything mentioning the group mean. So here we're going to add in something mentioning the group mean. And I can add 0. It's a math thing. You can always add 0. The specific version of 0 I'm going to add is minus the group mean plus the group mean. And if you quickly add those together in your head, you'll see that they cancel out and equal 0. So I'm just going to drop this in the middle. The left side of my equation represents where I started, the point minus the grand mean. The right side represents dropping this minus yi dot bar and plus yi dot bar right in the middle, right before the subtraction sign. What you'll see is I end up with y sub ij minus yi dot bar plus yi dot bar minus y dot dot bar. Now, if I want to break this down a little bit, think about what these mean. This was the total movement from the point to the grand mean. And we're saying this is the same thing as the movement from the point to the group mean plus the movement from the group mean to the grand mean. It's kind of nice because if you remember, what we were eventually trying to aim for is the movement between the group and the grand mean. This was the variability that we were going to study. It was the cool approach of ANOVA. And we said we were going to compare this to the movement within the groups. So now, through this little addition of this special zero, in terms of our base measure of variability, this isn't formal variance, this is just our base measure of variability, we can see that we can break down this movement, total movement of the points from the grand mean into these two components. The movement of the point to the group mean, this first one in parentheses called the within group movement, because again, it's just looking within the group. And then the second component, which is looking at the group means, those dotted lines, compared to the golden line, the grand mean. And this is the between group movement. This is the main thing we wanted to look at in ANOVA. Again, this within group movement is kind of our error. This is what we're looking at to determine the background white noise, to determine if this group movement is big enough to be considered statistically significant. So let's look at what these quantities look like on the graph. So first of all, we had our movement between the point and the group mean. We said we have the within movement, point to group mean. And I'm doing this for this top point, but you would have one of these for every single point on the graph. Point to group mean, point to group mean, point to group mean, point to group mean. So you'd have multiple of these. Then we had our second component, which was the between groups movement, and that's saying how far is our dotted line from the group to the grand mean. And now we would have one of these for each group. So for the first component, we have one for each dot inside of a single group. And that would be for y sub 3 dot, and then we'd go over to y sub 2 dot, and then do all that again for each dot within the second group. And then we would go to y sub 1 dot and do all that again. So we have for each group this breakdown. Here, though, we have each group minus the grand mean, each group's mean. So we'd have the dot, dot, dot horizontally here minus this grand mean gold line. We'd have this one minus the grand mean gold line. It'd be a very small quantity here. And we'd have this one minus the grand mean gold line. So that is our between groups movement component. Last but not least, we had the total movement in the problem. So we had the total data movement, the total distance between the data and our gold bar. So what we're saying is that the total amount of movement between the data and the gold bar can be broken down into two pieces: the movement between the data and the group mean, and the movement between the group mean and the gold bar, and that these add up to this total amount of data movement. So that's the graphical view of what's going on behind our notation here. So this makes sense for our individual point movement, I hope, when we're breaking down these that initial equation we discussed earlier, expression. But recall that our variance was calculated by squaring and summing the distances. This is an important component in ANOVA. We'll call it the sum of squares. You squared up those differences and then you summed them together, the sum of squares, or SS. The fundamental ANOVA identity is something that seems really straightforward, and I'll just say mathematically it's not. But ultimately, the fundamental ANOVA identity states that if I look at the sum of squares for the total movement, this is equal to the sum of squares within the group plus the sum of squares between groups. This is a really cool thing, that the relationships still work even with all of these differences raised to the second power and added up. Note that I'm adding up over both all of the groups and all of the people within each of the groups. So it's I shouldn't laud on this too much, but I'll just say This looks really easy. Hey, I just add a squared on the left and a squared on the right. But actually, mathematically, you can't just add a squared on the right. That doesn't actually work. Mathematically, you can't do that. And we have some pluses here. Those break everything down. So this proof actually demonstrating that this is true is actually a big deal. It's a little bit more work than it looks like, I guess is what I'm trying to say. It's not a straightforward thing, but it is a pretty cool thing because it lets us do this variability breakdown. Recall that the sum of squares was the numerator in our variance calculation. In this particular case, what we're saying is that the total amount of variability, that quantity on the left-hand side, can be broken into two components. Perfectly broken into, exactly split into two components. It can be broken into the component of the movement of the group means, the between group sum of squares, and it can be broken into the component of the movement inside of the particular groups. So when we add these together, we get the total sum of squares. And again, these are all variability pieces within our variability equation. So this is our big breakthrough. And again, this is ultimately what we're going to end up using in our analysis, is this idea, because we wanted to look at our between group variability, where we're going to start with the sum of squares here. This is going to be our jumping off point. And then we wanted to compare it to something, this total amount of variability not in the group. And what this is saying is that you can break down your total variability between these two things. There's nothing left over. The other thing that's kind of important here is there's nothing copied over between these. So these are distinct in terms of looking at our sums of squares. So I can compare them without worrying that I'm double dipping. All right. So let's see what this gives us. The ultimate analysis tool that we end up using in ANOVA is a table. And it's a table that's constructed through some things that we've talked about and some things that we haven't. Actually, we've already talked about most of the stuff that's going to go into here. And the table helps us keep organized in terms of our calculations. So we're going to start with the sources of variability. And again, we just mentioned that the total variability can be broken up into two places, the between groups and the within groups components. And I'm saying variability, it's a piece of the variability calculation, those sums of squares. But we can break this up into two different sources of this variation, again, between the groups and inside of each group. I should note here, I'm going to use notation that reflects between and within groups because it's a little bit more, I think, intuitive in terms of exactly what we're talking about as it relates to the pictures. But often notation referring to treatment and error is also common. And when we get to future analyses, I'll be using notation as relates to error rather than within groups. So just be aware of that as we go forward. So we already talked about our sums of squares between, our sums of squares within, and our sums of squares total. Here, I'm just writing out the sums of squares component. We had the total equals within plus between. That was our fundamental ANOVA identity. Here, I'm just writing those out in their place on the table under the heading sums of squares. So I have my total sums of squares, which I'll denote SS sub T, my within group sums of squares, which I'll denote SS sub W. And again, if I used error notation, I would call this SSE, which is very common. And for my between groups, I have SS sub B. And if I were using treatment notation, I would write SS sub T. And I say very common, both of these are very common. So this is definitely standard notation. So don't feel like we're using bizarre notation. I know that's a serious lifelong concern of yours, is whether the notation in stats class is completely kosher. But I promise it is. So this is standard notation. The only major one that you might see, again, both of these are sometimes used, SS sub TR for treatment, SS sub E for error. That one you'll see a little bit more often than SS sub TR, but you'll definitely see SS sub B and SS sub W as well. Okay. Moving on. Degrees of freedom. So degrees of freedom is going to become an important component within ANOVA. Degrees of freedom for the between groups effect or the treatment effect is found by taking the total number of groups and subtracting 1. So just like earlier we had n minus 1, here we have I minus 1. Degrees of freedom for the error or within groups is a little more complicated to calculate. Each group, or one way to think about it, is each group has j participants. So we're going to do j minus 1 within each group. And then if we add them up, so j minus 1 from the first group, plus the j minus 1 from the second group, plus the j minus 1 for the third group, we end up getting I j minus 1s. And the math way that we figure out how many total that is I times j minus 1. For the total degrees of freedom, we have I times j, which we also called capital N earlier, minus 1. And that's our total degrees of freedom for the whole analysis. I will note that just as the sums of squares between and within added to the sums of squares total, the degrees of freedom between and within add to the degrees of freedom total. Now that's only true for these two columns. The other two columns we're about to talk about, that's not true for. But for these two columns, we can add, in this case, degrees of freedom for between, degrees of freedom from within, and we would get the total degrees of freedom. All right, the second to last step is to calculate our, variance estimates. And I need to be careful because there are formal variance component estimates that we can do. But essentially, we have a sums of squares. We divide by our degrees of freedom. In a way, this is a variance calculation. If you did this with sums of squares total divided by degrees of freedom total, that's how you would get the sample variance for all of the data in the problem. I will say that calculation is not typically included in an ANOVA table, but it's important to realize that that's what we're doing. So when you think about this, think about we were calculating the numerator here. We found the denominator here. So now we're just putting numerator over denominator to get our what's called our mean squares, our average sum of squared values. In this case, again, I've denoted MSB and MSW. This one is a good one to write MSE next to. Again, SSE and MSE. These are things that are going to be very common. And again, in the ANOVA language, it's common to use between within for the sums of squares, degrees of freedom, mean squares, and our source of variation. In other analyses that we'll get to later in the course, I'm going to talk about mean squared error, and it's going to relate to a similar concept. So just something to consider jotting down here, not really for our lecture in this lecture set, but for future lectures on other analyses so that you can see the connections between all of these analyses. In any case, here, again, we're calculating essentially the variance between the different groups and the variance within each of the different groups. And what we said earlier was that we want to compare these two together. Now, in our means, we compared via subtraction problem. But in this case, we're going to compare via dividing the two. This final column, F, represents our F statistic, and this is our test statistic for the ANOVA analysis. Again, this is literally the variance from between the groups, looking at how much variability the groups are showing, as we talked about in the beginning, dividing by the variance from not between the groups. Again, we call this variance within or error. And this is exactly what we're going to analyze when we analyze our test to determine if the variability between the groups is statistically significant. That is, if it is far enough greater than the variability within the groups to represent something that suggests that there is a difference between these groups. And again, what we're saying is if there's variability in the group means, that implies that there is a difference between the group means. That's the logic of ANOVA. So this is our calculation table. In a computer output, this will often include a p-value column on the right-hand side. And we would make our decisions as always. We would either use the p-value and then compare to the alpha level to determine statistical significance. Often alpha equals 0.05. Recall, if p is less than alpha, it's a significant finding. We reject the null hypothesis. If p is greater than alpha, it's a non-significant finding. We fail to reject or don't reject the null hypothesis. We're kind of left at that starting place, left at that default value of the null hypothesis. So we can use that p-value, but we can also use this test statistic as we have before. We compare the test statistic to the critical value. And if our test statistic is greater than the critical value, then we would reject the null hypothesis. If the test statistic is not greater than the critical value, then we fail to reject the null hypothesis. So here I am talking about ANOVA hypotheses, but we haven't even talked about what those darn hypotheses are yet. So let's cover that. In ANOVA, again, we're testing if there's any variability between the means of the groups. And again, the logic of ANOVA is if there is variability, then there is a difference between the means of the groups. That's what we're doing. So the hypotheses in word form can be written as our null hypotheses is that there's no difference between the groups, which would lead to no variability among them. And the alternative hypothesis would be that there is a difference between the group means. Now, I write these out in words. It's important to realize there is a equation that we can use to express this with a little bit of logic notation. That's not as much important to understand. The reason the hypotheses themselves, at least in word form, are important to understand is recall this is what our statistical decisions are regarding. Is this a reasonable claim? Do our data align, or are our data compatible with this claim? Ultimately, that's what our p-values and test statistics are testing. How compatible are our data with the claim that there's no difference between group means? And if there's not very much compatibility between our data and that claim, what we end up determining is that we need to reject this claim. This claim seems to be incorrect. And if this claim's incorrect, then kind of by logic, this second claim is what we're assuming is correct. So we're determining evidence of the alignment between our data and this null hypothesis. Because of that, the null hypothesis has a direct bearing on the decisions and conclusions that we make with the inferential statistics. So understanding what your null hypothesis is and what your alternative hypothesis is actually very important in making the right conclusion with an inferential statistical test. Again, a significant result here, and that is the rejection of the null hypothesis, tells us there is a difference between the means. But note that it doesn't tell us where that difference is. So if I've got multiple groups, it doesn't tell me which one is better or which one is worse. We'll address that later on in this lecture set. But it is important to realize that this is a bit of, I don't want to call it a limitation, but it's something to know. ANOVA tells you that there's a difference, but not where the difference is. And so it's important to be aware of walking into the analysis. All right, well, let's jump into an example. So within this lecture, we won't be doing any hand calculations. I'm not going to make you calculate sums of squares by hand, certainly not to follow along with the lecture video. But because of that, there's not really any examples that you'll need to work through. So I'm just going to keep this simple. I'll have a single example to demonstrate the concept, and then we can move on. So in this example, I want to consider one we're looking at different nursing education programs, and we're assessing the National Council Licensure Examination, the NCLEX. The programs that we're going to be comparing are going to be a lecture-based program, which we'll call didactic, a simulation program, which we'll call experiential, and a field-based learning program, which we'll call service learning or CSL. So the thought behind this problem is, if you've ever heard somebody say that, oh man, folks from this school are great, or man, this program's so much better at teaching this, or things like this, we'd like to assess if that's actually true, rather than just assuming that, what type of program you went to is going to necessarily make you a better practitioner. Let's at least assess the degree to which that's true. And I mean, there's a bit of a question here in terms of whether the NCLEX is the correct tool to implement that. And that's a fair debate. But without loss of generality, you could do this with any assessment that you feel is more accurate to individuals' ability. So quick note, and then this is a bit of an aside. Some of you are already going to be familiar with this, but some of you, this might be helpful. Why would you do this? So let's say we're doing this as an administrator. We want to look at new nurses coming out of programs to see who's going to succeed best in our system. And again, whether or not this particular outcome is a valuable proxy, that just means replacement for that desired true outcome is up for debate. And the better of a proxy it is, the more valid this question is going to be to that purpose. That is, the more valid the evidence you present from this inferential test is going to support your statistical story. But consider, why use data at all? Why not just data don't perfectly capture people, and we already know where the best people come from, right? Well, I mean, at some level, the reason that we implement data-driven procedures is to remove a lot of biases that can be made in these determinations. Sometimes we just happen to notice people from some programs and not others. Sometimes that just becomes a little bit more of an obvious thing, not because the work is better, but because the people talk about the program more. This background data is extremely important to adding evidence to these statistical stories to make more compelling cases than something like, because I just know this to be true, or because I say so, or because so-and-so told me, or maybe so-and-so and I both noticed this to be true. Those are not very good reasons. Those aren't very sound rationales, and those are highly prone to bias. So this process, I mean, I don't want to imply this is completely bias or error-free. It's not. However, it does remove a lot of the potential bias that's implemented in other different types of processes, and that would be a good reason to implement a method like this. All right, so for the sake of fun, and this actually isn't what happened in the study, but we're just going to assume students were randomly assigned to programs. So again, that didn't actually happen. We're going to assume this is a proper experimental design, and that'll let us get some practice doing some interpretation with causal connections, which will be a little bit fun. So we're going to assume that all of the things regarding that has been met. I know we've been not doing that previously, but hopefully that'll help us have some more fun interpretations in this case. So at the alpha equals 0.05 level, determine if the type of program has this impact. And again, note, I can use the word impact here. If we have the ability to talk about causal connections, if the study has been sufficiently well designed for an experiment, then we can do that. That is not implied with an ANOVA. That is not required for an ANOVA. That's something that's completely independent of an ANOVA. We could remove that second bullet point. We'd have to temper our conclusions a little bit, and the analysis would still run. We're still fine. But that's something that we're just dropping into this example for a little bit of fun with interpretation to keep things lively. All right, so our hypotheses for this problem, for the null hypothesis, the default skeptic belief is there's no difference between the mean scores of the students from the different program styles. And the alternative hypothesis is that there is a difference between mean scores of students from the different program styles. Sometimes you'll see average instead of mean used. That's fine. Average is a little bit ambiguous. We had multiple averages, mean, median, mode. Here, we're just being a little bit more intentional about which one we're specifying. So as I mentioned earlier, we're not going to be doing computations here. They're rather lengthy. We should have some videos associated with this lecture set that can demonstrate them. But in terms of this lecture video, we're just going to look at computer output from these to practice the interpretations. So below is a table produced by some software. I used a different software for this one just to change things up a little bit. The p-values on the right. So here we have our ANOVA table. I have my sums of squares calculated for my between groups, within groups, and the total sums of squares. And if you want to, you can add these up and confirm, hey, between plus within equals total sums of squares. I have my degrees of freedom between groups, degrees of freedom within groups, and again, I can add them to be total, the total degrees of freedom, and I can double check that quickly. Now, sums of squares in and of themselves are not interpretable. Oh, this is 24,000. That's huge. That's a huge amount of error. Well, no, it's just really not interpretable in any way. So we largely ignored the sums of squares. If I got, and I was about to say I guess this is 240,000. I was about to say if I got really large values, I might be concerned. But hey, 240,000 might be really large to somebody. So here, I think I'd get concerned if I had like 99999999999 here as a quick error check. That I'm not sure I've ever had that happen. I might have had that happen once and realized I messed something up when typing in the data. So sums of squares, not too concerned about, mostly because they just don't have an interpretation we can walk away with. With that said, the degrees of freedom. This one seems weird, I feel like, to many students, but the degrees of freedom are actually a really useful place to check in. I look at 2 degrees of freedom. I look at the between groups degrees of freedom and the total degrees of freedom. I look at the between groups degrees of freedom to make sure that the computer software read in my analysis correctly, and or if I'm getting a report from somebody else, that they ran their analysis correctly. This is a way, and it doesn't happen all the time, but there will be cases in a meeting where somebody hands me a report and I'll glance at that and I can quickly suggest, hey, this was implemented incorrectly. Or you left a group out or something like that. And individuals might say, oh my goodness, how can you just look at all these numbers and know? And the answer is, I'm not looking at all these numbers. I really look at 2, at least in these first couple columns. I look at the between groups degrees of freedom and the total. The between groups degrees of freedom tells me how many groups you had. I take this number plus 1, so I got this number by taking I minus 1. I take this number plus 1, and that tells me the number of groups. So this is indicating I had 3 groups. Now in this analysis, where we're comparing didactic learning, experiential learning, and service learning, it does make sense that we have 3 groups. This is a good double check that says, yes, things are coming out right. But I have had, probably a dozen professional cases where either I or someone who handed me a report had this incorrect. Now, I've probably looked at probably over 100 of these, so that doesn't mean that they happen particularly often. Gosh, I don't, probably many hundreds of these now that I'm thinking about it. So that doesn't mean that these errors happen particularly often, but it is a very quick double check to quickly add 1 to your between groups degrees of freedom and compare it to the problem that somebody mentioned they were trying to solve. Often, even if it's not a formal error, it'll bring in clarification. Oh, we had to exclude several groups because they didn't have the sample size to be included. Okay, good to know. And if somebody doesn't mention that in their report, it can be really important to hear, okay, we studied the male sex, we studied female sex, but then we didn't include the other sexes that were listed because they didn't have the sample size to support inclusion. And that's just really good to know that we excluded everybody else and we only have those 2 groups listed. Or we studied these particular races, but we excluded the other ones because we didn't have the sample size. How do I know that somebody was excluded? Because, hey, we had 6 racial categories, but your degrees of freedom reads 2, indicating that you only ended up using 3 groups. Where did the other 3 groups go? Sometimes there's a really good answer. Many times there's a really good answer. But to be able to ask the question in the first place by simply glancing at a single number is pretty handy. So this is a good double check number for me. The other good double check number is this second one. Recall that this is one less than the total sample size. So if I add 1 to this total degrees of freedom, I get the total sample size. In this case, we had 313 participants participate in this study. And I can quickly double check, does that sound right with everything else that's been reported if I'm reading a report, or does that seem right with the data I tried to read in if I'm analyzing this myself? Again, this is a great double check. Both of these are fantastic double checks, both as analysts when you're running this and as consumers of research, to make sure that you're following along with what's being presented and can isolate some very poignant, specific, and insightful questions to ask about some details of the analysis that can drastically change the interpretations. All right, so we've got our mean squares components. Mostly what I look at these for is to make a mental double check, and this is happening on a computer. So I actually do double check this often, just mentally, that this mean square between divided by mean squares within gives me my F value. But again, it happens on a computer. This has always been true. In this case, I get an F value of 10. And then I get my statistical significance, and I note here in this particular software, they don't write P, they write sig to represent the P value. So I don't really necessarily interpret the mean squares. If I have a critical value, I might interpret F, but I don't on hand. And that's why most people like the P value for interpretation, is most people don't have a critical value on hand and don't want to go to software to interpret the results. They just want to go to the table. And here with the P value, I can interpret this. For me, the interpretation, I compare the P value to alpha. So in this case, if I'm using alpha equals 0.05, P is less than 0.05, indicating that there is a statistically significant effect. So we reject the null hypothesis. Recall what that means. The null was that there's no difference. We reject that, meaning there is a difference. We conclude that there's evidence that there is a difference between the groups. Again, a statistically significant effect. Sometimes we call this a statistically significant difference between the groups. A natural follow-up is, well, which groups are different, or are all of them different? And the answer is shrug. I don't know. That's not what analysis tells me. Analysis tells me that there is a difference between the groups, but does not suggest where the differences is. That is, we don't know where the difference between the group lie. We don't know which group is better. Again, we're comparing community service learning, we're comparing experiential learning, and we're comparing didactic learning. So we need to figure out which ones are different from one another. Now, we're going to talk about this in more detail in a moment. But to tie back to our statistical storytelling chapter where we discussed the power of graphics, graphics can be helpful. Here I have, I believe, Group 1 is community service learning, Group 2 is experiential learning, and Group 3 is didactic learning. And I can see the graphical comparison of my test scores in this example. I see didactic is the worst, experiential is kind of in the middle, and community service is better. But this still leaves a question. Is community service better than experiential learning? Are these similar? Is experiential learning better than didactic? Could the only difference be community service and didactic? Is that even different? And that is an open question. So we can kind of get a feel for it with our graphics, but in terms of exactly which ones are statistically significantly different, that does not come from our graphics. We're going to need some additional information to calculate that. And that's what we'll be talking about in the next video in this lecture set, is the additional information, which we'll summarize as post hoc analyses.